Okay, in this video we will be doing the last topic in Med 1, which is the methods. The method of maximum likelihood, or the maximum likelihood method. Okay. It is one of the methods actually. One of the methods to estimate the population parameter theta. Okay, and it is denoted by MLE in short. Okay, so in exam, if the professor asks for MLE, you must know that it is the maximum likelihood estimator. Okay, so first introducing this MLE. Okay, so what is an MLE? MLE, like the other estimators, is a statistical technique or method for estimating the parameters of probability distribution. By maximizing, this is the difference, okay, between the other one, which was the method of moments, and this one. Okay, in method of moments, what we did was we found the sample moments and then compared it or equated it to the population moments. Okay, and then find the estimator theta bar. But here, MLE, we find the estimate of the parameter of the probability distribution by maximizing the likelihood function. The likelihood function, capital L of theta. Okay, I will further introduce this maximum the likelihood function also, and I will share the detailed steps how to do it. Okay, so there are some reasons behind using this maximum likelihood estimator. Okay, the foremost reason is that it provides, the first thing in pros actually, sorry, not cons, pros, the advantages of using this method is, the first thing is that it provides efficient and unbiased results. Okay, the second thing is that it is optimal, and optimal in a sense, asymptotically optimal. And we know that it is for when the sample size is such large, up to infinity, then the MLE or theta bar actually has a true value theta, which is equivalent to the population parameter that we want to find, whether it be mean, variance, or anything. Okay, parameter can be anything. So it is asymptotically optimal. It means that for large sample size, severely large, like going up to infinity or to the maximum, then when we estimate the theta bar, it is equivalent to the population parameter. Okay, it pinpoints it as a true value theta, which is equivalent to the population parameter that we want to find, whether it be mean, variance, or anything. Okay, parameter can be anything. So it is asymptotically optimal. It means that for large sample size, severely large, like going up to infinity or to the maximum, then when we estimate the theta bar, it is equivalent to the population parameter. Okay, it pinpoints it. And the other thing is that it very well fits or works well in different statistical models. Okay, and by these statistical models means that we know that we have like probability distribution functions, okay, PDFs or PMFs for a sample, because we take a sample, for example, we have x1, x2, x3 up to xn. Okay, we have these variables. Okay, from a sample, this is a sample that we take from a population, and that population has some probability distribution function. Okay, for example, this probability distribution is exponential. Okay, so this follows the exponential distribution. Okay, similarly we can have like these samples taken from the gamma distribution. Okay, similarly from binomial distribution and so on. Okay, so the sample can be taken from any population, okay, that follows certain distribution or have certain distribution function. Okay, so each of them has different probability distribution function PDFs. Okay, all of them have different PDFs, probability distribution functions. Okay, so it can tackle a variety of different statistical models. Okay, and works fine with estimating theta bar, which is the true representation of population parameter theta. Okay, so the maximum likelihood estimator is a statistical technique for estimating the parameter of probability distribution, okay, by maximizing the likelihood function capital L of theta. I hope you understand it. Okay, we will have like certain function, okay, based on this probability distribution. Okay, depending the sample that we took from a certain population, okay, it will have different probability distribution and will have a different maximum likelihood function, okay, which depend on this probability distribution. So these are the pros or the advantages of using this method. It certainly has like one very big con, or we can say that disadvantage. Okay, and that disadvantage is that it is very computational complex. Okay, computation wise it is very complex. It involves rigorous computation if the statistical model is complex. Okay, for normal functions it may work like very fine, you may have like very short computation, but for complex functions it is very computational. The computations behind finding the theta bar in MLE is very complex. So this is the only disadvantage that it has. Okay, I will explain the capital L of theta, and the basic concept of using this maximum likelihood function in the next video. Okay. Okay, so now going towards the basic concept or understanding the basic working of MLEs. Okay, now we will understand how this method actually works. Okay, so for that, we have a random sample with elements like x1, x2, x3 up to xn. We have these elements in a random sample. Okay, and we have this sample from certain probability distribution, PDF, or probability mass function. PMF. Okay, it means that this sample follows certain distribution which has a distinct or definite probability density function or probability mass function. We know that each the random sample taken from certain population follows certain distribution. Okay, and that certain distribution has different the PDFs or PMFs. Okay, so these PDFs and PMFs or this data has a population parameter theta. Okay, this is the main thing. Okay, this is a population parameter theta. Now we want to find this population parameter theta, but how to find it? We actually use this sample data, okay, and impersonate that this sample data is from the true population, okay, and the theta bar that we will estimate actually from the sample data or sample population actually gives us the value of the true population parameter theta, are equivalent to the true population parameter theta. So what we do in here is, like all the methods in statistical methods actually, what we do is we estimate theta bar from the sample data and it gives us the value of the true population parameter theta. Okay, so the MLE or maximum likelihood function works also in the same way or the same concept. Okay, so then the likelihood function L of theta, capital L of theta, is defined as capital L of theta is equal to the probability of x1, x2 up to xn condition on theta. Okay, it means that we have a certain probability that these sample points are taken from this population which has the population parameter of theta. Okay, so since we assume or we are given that all the random observations which are x1, x2, x3 up to xn, they are independent of each other. In Poisson process actually, or in the statistical methods, all the random observations which are x1, x2, x3 up to xn, they are independent of each other. In Poisson process actually, or in the statistical methods, these observations are independent of each other. Okay, so the capital L of theta is the product for I is equal to 1 up to n of this individual probability density function. Each of this x1, x2, x3 up to xn has some density function. Okay, so the likelihood function L of theta is equal to the product of these individual density functions, such that it is taken from the single population which has a population parameter of theta. Okay, so what this represents is, this represent the product or multiplication of individual probability density functions, PDFs. Okay, and the individual PDF is denoted by f of xi condition on theta for all x1, x2, x3 up to xn. Okay, and why we do the the product? Because we know that, just I wrote over here, that all the random observations x1, x2, x up to xn are independent of each other. So this independence of each other actually, it gives us the opportunity, okay, to calculate the joint, this is the joint probability density function, okay, L of theta, and it is the product of the individual probability density functions for each x1, x2, x3 and up to xn, from I is equal to 1 up to n. Okay, so this is what the maximum likelihood function is. Okay, capital L of theta is equal to the product of the individual density functions, such that all of them are taken from a single population which has the parameter theta. Okay, so this is the likelihood function. Now we will maximize this likelihood function. Okay, and how we do it? We do it using the logarithmic functions. Okay, we will take the log of it, okay, to untie this thing, and once we untie this thing, then we will take the differential of it and put it equal to 0. So we will get the theta bar out of that thing, and that theta bar is the value of the estimate that actually represents, that maximizes the likelihood that this theta bar represents the theta, the actual population. Okay, I will explain this step by step when I go from one point to another. Okay, so this is the maximum, this is the likelihood function, and we will now maximize it. Okay, and we will do this maximization using the log likelihood function. Okay, we will use log to untie this multiplication and convert it into summation. Okay, and then from that summation we will take the differential of it with respect to theta, and we will calculate theta bar. Okay, so I will do the log likelihood function to find theta in the next video. Okay, so now the only thing that we need to do is we need to find theta, okay, and we need to estimate it using the theta bar. Actually, we need to find theta bar, so it impersonates or it represents the actual theta. And how we do it? We actually do it by maximizing this function, okay, and by maximizing, we actually get the probability that we have this x1, x2, x3, taken from this same population which has the actual parameter theta. So to find theta, what we use is we use log likelihood function. Okay, and what we do is we apply log on both sides. So ln of capital L of theta is equal to ln of the product of I is equal to 1 up to n individual functions such that they are taken from this population. So what it does is it gives us small l of theta, which is the log of the capital L of theta, okay, and it is equal to summation of I is equal to 1 up to n log of f of xi theta. Okay, so we apply log to the individuals and add the results of those. Okay, so ln of theta is equal to summation of from I is equal to 1 up to n the individual log of this PDFs for each I is equal to 1, 2 up to n. Okay, so what we do is we apply log to individual PDFs, okay, and then add it, so it will give us small l of theta, which is the log likelihood function. Okay, so MLE theta bar, actually it is the value of theta which maximizes small l of theta. Okay, and theta bar or the estimate is equal to d by d theta of L of theta. Okay, so we make this partial differential with respect to theta of this log function, and it gives us a theta bar. Okay, so that is how we actually find the MLE estimate. Now I will do a few examples so that you understand how the basic process actually works in the regular exercise problems, or you will find out how we do it in exam. Okay, so I will carry on the examples in the same video. Okay. Okay, so we have an example, okay, and it says that let's x1, x2 up to xn are random observations from an exponential distribution. It means that the population is following the exponential distribution. Okay, so the PDF of the exponential distribution, actually f of x such that lambda, okay, because lambda is the parameter over here. Okay, whenever we have exponential distribution, the parameter is lambda, so f of x such that lambda is equal to lambda e raised to power minus lambda x. Okay, for all x greater than 0. Okay, this is the PDF for the exponential distribution. Okay, so what we want to do is we want to estimate this lambda using MLE, okay, or lambda bar. So what we need to find is lambda bar, and it estimates the value of the true lambda. Okay, so step 1 is to have the likelihood function L of theta or L of lambda over here. Okay, so the capital L of lambda is the product for I is equal to 1 up to n of this PDF, okay, which is lambda e raised to power minus lambda x. Okay, and here x will be, it will have a subscript of I, because I is equal to 1 up to n, and we have n number of random observations. So that is why this is for a single x. Okay, this is a sample, only one sample taken from. Now there are n samples. Okay, so we will have xi for I is equal to 1 up to n. Okay, so the likelihood function, first of all, you need to do is you need to have like this PDF. Okay, this is very important. Understanding the PDF, the teacher must have given you handouts for these PDFs. Okay, which is a supportive thing for your exam. Okay, you must have a sheet that have all the PDFs and PMFs and CDFs for the each population, okay, or each distribution. Okay, so picking the distribution from that, the PDF, putting the PDF of that distribution over here. For example, here we have exponential distribution, so from that sheet we will pick this lambda e raised to power minus lambda x. Okay, and we will put it over here. We will understand from that sheet that the probability distribution for the exponential distribution is this thing. PDF is equal to this thing. So now putting it equal to L of theta or L of lambda, because we have lambda over here as parameter, so we will skip this theta and put lambda instead. Okay, so capital L of theta is the likelihood function, and it is the product of individual PDFs. Okay, for I is equal to 1 up to n, because we have n observations. Okay, so for each observation we have an individual PDF. Okay, so now the step 2. In this step we take the log likelihood function. Okay, we will convert it into small l. Okay, so ln of capital L of is equal to ln of this okay, so it will give us the result it is equal to small l of lambda. Okay, so putting here, okay, so small l of lambda is equal to summation of I is equal to n log of lambda, log of this function. Okay, okay, this log will, this is an addition property, or we can say that, whenever we have like ln of a cross b, so it is equal to ln of a plus ln of b. Okay, so here this logarithm, it will go inside and this product will be converted into summation. Okay, that should be understood. Okay, this is the property that we use. Okay, these are the basic properties and you need to understand it. Okay, the division is converted into subtraction and multiplication is converted into addition when we apply log. Okay, so here is the small l of lambda is equal to, now if we apply log to this lambda and this separately actually, okay, so it will be equal to this thing, summation of I is equal to 1 up to n log of lambda minus lambda into summation of I is equal to 1 up to n of xi. So opening this, as this summation is equal to n, so we have n ln of lambda minus lambda into summation of I is equal to 1 up to n xi. Okay, so this is small l of lambda. Now we apply the differentiating with respect to the parameter lambda. Okay, we will differentiate it with respect to that particular parameter. Okay, here we have lambda, so d by d lambda of L of lambda is equal to d by d lambda of n ln of lambda minus d by d lambda of lambda summation of xi for I is equal to 1 up to n. Okay, now as the differential is partial, okay, so it will be equal to n into d by d lambda of ln of lambda minus summation of xi for I is equal to 1 up to n d by d lambda of lambda. Okay, so it will give us this will be equal to 1 actually. Okay, and it will be equal to 1 over lambda. Okay, so what we get is we get n into 1 over lambda minus summation of xi for I is equal to 1 up to n. Okay, so when we get this, we equate it to 0. Okay, I will continue this in next video. So equating it to 0, what we get is we get n by lambda minus summation of xi for I is equal to 1 up to n is equal to 0. Okay, so this lambda, okay, if this is negative, so it will get into this direction, so it will become positive. So n by lambda is equal to summation of xi for I is equal to 1 up to n. Okay, and this n is in the numerator, so when it converts to this direction, it will become denominator. So 1 over lambda, it will be equal to summation of xi for I is equal to 1 up to n divided by n. Okay, now inverting this whole, for example, we call it A. So inverting A, we get, when we invert it, it will become lambda, okay, and this will become n divided by summation of xi for I is equal to 1 up to n, okay, and it will be equal to the estimate lambda bar, okay. So the MLE or lambda bar is equal to n divided by summation of xi for I is equal to 1 up to n, okay, and we can write it as 1 divided by summation of xi for I is equal to 1 up to n divided by n, okay. This is equivalent to this thing, and we know that summation of xi for I is equal to 1 up to n divided by n is equal to x bar. So it is equal to 1 divided by x bar. So lambda bar is equal to 1 divided by x bar. This is the MLE for this exponential distribution, 1 divided by x bar, okay. This is the estimated value. So in this video we will be doing one exercise question, which is on page number 326, okay. Let me show you the question, okay. This is the exercise 6.1.1, okay. It is regarding maximum likelihood methods, MLE, okay. So the question states that the exercise is 6.1.1, okay. It is in the reference book, which is written in the syllabus, okay. So we have, let's x1, x2 up to xn is a random sample taken from gamma, where alpha is equal to 3 and beta is equal to theta distribution, okay. And we have the range of theta is between 0 and infinity, okay. This is the range of the theta. They want us to calculate the MLE of the theta, or the expected value of this theta. So we have like a few steps to follow when we do the MLE. The first step is to identify the distribution, okay. In this case it is gamma distribution, okay. Whenever this sign comes, it means that it is gamma distribution, and it has two parameters, alpha and beta, okay. Alpha is the phase and beta is the scale, okay. So the second step, this is the first step. The second step is to write down the PDF, the probability density function, which is the f of x of when we have the parameters as alpha and beta, or the functional value of x when it is taken from the gamma distribution. It can be, written in both kinds, okay. So this thing, f of x, the individual PDF for each x1, x2, x3 and so on, it will be equal to x raised to the power alpha minus 1. This thing is understood, okay. This thing, okay, when we have gamma distribution, it must be given to you, or you should memorize it, okay. So x raised to the power alpha minus 1 multiplied by e raised to the power minus x by beta divided by beta raised to the power alpha multiplied by this sign, the gamma sign, into alpha. Now this thing has a significance over here, okay? I will explain this. This of alpha, okay, let's suppose this is T of alpha, okay? So it is done in two ways, okay? Two ways possible. Its value can be done in two ways. When the first thing is when alpha is equal to integer, like in this case 1, 2, 3, 4 and so on, okay? When alpha has integer value, and B is when alpha is continuous. It means that it has a value of 0.5, 0.8, 1.9 and so on, okay? We have continuous value. So in this case alpha is equal to 3, okay? So in the first case T of alpha, it is equal to alpha minus 1 whole factorial. But in this case it is equal to integral of 0 up to infinity t raised to power alpha minus 1 multiplied by e1, okay? We have continuous value. So in this case alpha is equal to 3, okay? So in the first case T of alpha, it is equal to alpha minus 1 whole factorial. But in this case it is equal to integral of 0 up to infinity t raised to power alpha minus 1 multiplied by e raised to power minus t dt, okay? So remember that if we have like alpha is integral or integer or it is continuous, so depending on that we have to define this factor which is T of alpha. So here alpha is equal to 3, it means that it is integer, so T of alpha, it will be equal to alpha minus 1 whole factorial. So putting the value over here, so the individual function taken from this beta distribution is equal to x raised to power alpha minus 1 e raised to power minus x by beta divided by beta raised to power alpha multiplied by alpha minus 1 whole factorial. Now we have the value of alpha is equal to 3 and beta is equal to theta. So putting these values, so what we get is f of x such that alpha is equal to 3 and beta is equal to theta, it is equal to x raised to the power 3 minus 1, okay, e raised to power minus x by theta, theta raised to the power 3 and 3 minus 1 whole factorial. So it will give us x raised to power 2 e raised to power minus x by theta, theta cube, and 2 factorial will be equal to 2 factorial will be equal to 2. So we can get an actual value of e is equal to minus x by theta, theta square multiplied by 2. So this is the individual PDF of x when we have alpha is equal to 3 and beta is equal to theta. So this is the individual PDF. Okay, now we have a third step. The third step is step 3 is the maximum likelihood function, which is capital L of theta. So capital L of theta is equal to the multiplication of these individual f of xi slash 3 and theta. Okay, I write it xi because we have x1, 2, 3, 4 up to xn. Okay, so from I is equal to 1 up to n we have the multiplication of these individual probability density functions. Okay, so it will be equal to, putting the value of this individual function, okay, this one we write it over here, so it will be equal to multiplication of I is equal to 1 up to infinity x square. I will write it xi square now over here, okay, because I is equal to 1 up to n, e raised to power minus xi divided by theta divided by theta square multiplied by 2. Okay, this is the likelihood function, capital L of theta. Now what we do is we open this thing, okay, because over here the 2 theta square in the denominator, it is constant. Okay, the denominator is constant and the numerator is variable because we have xi value, so it will be having a different value for I is equal to 1, 2, 3 up to n. Okay, so the numerator is variable but the denominator is not variable, it is constant. So this multiplication will not be applied on the denominator because it is constant, it will be only applied to the numerator. So let's open it. I will continue this example in the next video. Okay, so capital L of theta, which is the likelihood function, is equal to multiplication for all the individual functions, okay, and the individual function is equal to xi square e raised to the power minus xi divided by theta divided by 2 theta cube. Okay, so the numerator is variable, so this function will be applied on the variables, but the denominator is equal to constant. This 2 theta square, 2 theta cube is equal to constant. So this product will not be applied on this. So when we open it, we get capital L of theta is equal to 1 divided by 2 theta cube into product of xi square and e raised to the power minus xi divided by theta. So this is the thing that we get up till now. Now we have another step, which is step 4, and what we do in step 4 is we apply the log likelihood, okay, to convert this product into summation. Okay, so natural log of capital L of theta is equal to small l of theta is equal to log of 1 over 2 theta cube into product of I is equal to 1 up to n xi square e raised to power minus xi divided by theta. Okay, so small l of theta is equal to, now applying log on both these, so here we have multiplication over here. Okay, so when we make this log, natural log, it will be converted into addition. Okay, so one mistake that I did is here we have the power of n, because here the total is n, so it applies on the denominator also, but denominator is constant, so we took it outside and apply this power of n. Okay, so that is one mistake that I did earlier. Okay, so now when we apply this is raised to power n. Okay, so when we apply a log, this power will become n forward. Okay, so it will be ln of small l of theta is equal to n into ln of 1 over 2 theta cube, okay, plus this multiplication will be converted into plus, okay, and ln of I is equal to 1 up to 1 xi square e raised to power minus xi divided by theta, okay. So small l of theta, it will be equal to n, and this when applied, okay, will give us n ln of 1 over 2 theta cube, okay. Now these two are multiplied, but over here, okay, we have a division, 1 divided by 2 theta cube. So the log has a property, when applied to a by b, it becomes ln of a minus ln of b. So here a is equal to 1 and b is equal to 2 theta cube. So it will be equal to ln of 1 minus ln of 2 theta cube, okay. So this property will apply to this thing, okay, plus ln of, let it write, I will open first this thing and then I will open the other thing also, so you understand, okay. Now opening this one only, so it is equal to n into ln of 1, okay. This n is for both, so we can write n for both of them, okay, minus ln of 2 theta cube. Now here we have multiplication, 2 into theta cube, okay. So here it will be converted into addition, okay, plus ln of I is equal to 1 up to n xi square e raised to power minus xi divided by theta. First I need to do this and then I will come to this, okay. So it will be equal to n ln of 1 minus n ln of 2 plus n ln of theta cube, okay, because n applies on all of these, so I have written n against everyone, okay, plus ln of product of I is equal to 1 up to n xi square e raised to power minus xi divided by theta, okay. So log of 1, log of 2 and log of theta cube, okay. So n natural log of 1 is equal to 0, so it will be equal to n into 0 minus ln of 2 plus this power will come forward, it will become 3n ln of theta, okay, plus this log when applied inside, it will become summation, okay, product will become summation I is equal to 1 up to n ln of xi square minus this 1 over theta is constant, so 1 over theta will become outside and it will become summation of xi. Okay, one mistake that I did is this minus is applied on both 2 and theta cube, so it will become negative, okay. This is minus n ln of theta cube and this is minus 3n ln of theta. This is minus, this is not plus, okay. Other than that it is okay. If in case you are wondering, minus ln of 2 plus ln of theta cube, so minus into plus will become minus. Okay, so minus ln of 2 minus ln of theta cube. Okay, so that is how I did it. Okay, and if you are wondering how we get this, okay, we get this like, let's ignore this step. Okay, I will write the from this n ln of 1 minus n ln of 2 minus n ln of theta cube plus ln of the product I is equal to 1 up to n xi square multiplied by e raised to power minus xi divided by theta. Okay, so now this natural log ln is multiplied on both of these, and here we have a multiplication over here, we have a multiplication sign over here, so it will become plus. Okay, so it will become n ln of 1 minus n ln of 2 minus n ln of theta cube will become minus n multiplied by 3 ln of theta plus ln of xi square, and we have product over here, so it will also become positive. Okay, and it will we have ln of e raised to power minus xi divided by theta. Okay, n ln of 1 is equal to 0, so it will become 0 minus n ln of 2 minus 3n ln of theta. Okay, plus now here we get summation of I is equal to 1 up to n ln of xi square. Okay, plus this is xi square. Okay, ln of natural log of xi square. Okay, plus log of this is equal to like ln of e raised to power minus x, for example. Okay, let's get put minus x I divided by theta is equal to minus x. Okay, so when we apply log over here to something e raised to power minus x or something e raised to power something, then it becomes minus x only. Okay, only the power. So here the power is minus xy divided by theta, and we have a product over here which converts into summation, so we will have summation of xi raised to power n up to the n minus xi divided by theta. We get only the power of e. Okay, when we apply natural log to e raised to power something, so we get only the power of e only. Okay, and as we have product over here, it will be converted into summation, which is the rule of the natural log. Okay, so we get minus ln of 2 minus 3n ln of theta. Okay, plus summation of I is equal to 1 up to n ln of xi square minus, okay, plus and minus, this will be when this negative comes outside, so it will be multiplied with plus, so plus and minus will become minus, and it will become summation of xi divided by theta. So this is the final answer for the small l of theta, which is the log likelihood function. Okay, now we will differentiate it. Step 5 is to differentiate with respect to theta, because theta is our parameter. So taking the differential of L of theta with respect to theta. So let's take the differential. I will continue it in the next video. Okay, so step 5 is to take the differential. Okay, differential. Now we need to take the differential of this final thing that we got over here, which is small l of theta. Okay, so d by d theta of small l of theta is equal to d by d theta of minus ln of 2 minus 3 n ln of theta plus summation of I is equal to 1 up to n ln of xi square, okay, minus summation of xi divided by theta for I is equal to 1 up to n. Now when we differentiate it, okay, this is ln of 2, okay, so let's differentiate it. Okay, so we are differentiating. Remember that this is a point to be remembered, okay, let me write it over here. Remember that we are differentiating with respect to theta. So what we do is we only take those factors which have theta, only those are differentiable. Like here minus n of 2, it doesn't have any theta, so it is not differentiable with respect to theta, so it will yield a value of 0. Here we have minus 3 ln of theta, so it is applicable. Here in the third factor we have ln of xi square, there is no theta over here, so it is not differentiable. In the fourth factor we have summation of xi divided by theta, we have a theta over here, so it is differentiable. Okay, so remember this point. Only the factors which have this particular parameter theta, okay, those are differentiable. So what we get is, we get d by d theta of minus 3 ln of theta minus summation of xi divided by theta for I is equal to 1 up to n. So only these two factors are differentiable. So when we differentiate it, what we get is, okay, minus 3, okay, into d by d theta of ln of theta minus, okay, now in this case we have this, the numerator actually it is not of a concern because it doesn't have any theta, so we will, what we do is we will put it outside of the differential and we will differentiate 1 over theta only. So what we get is minus 3, and when we take the differential of log of that particular, so it will yield 1 over that particular variable. For example, we take d by dx of ln of x, so it will yield us 1 over x, okay, this is the property of the differential. So here it will yield 1 over theta, so and this is 3n, okay, this is 3n, it is not only 3, this is 3n, because here we have 3n, so I mistakenly wrote it 3 only, so 3n ln of theta, so 3n will become outside and d by d theta of ln of theta, which becomes 1 over theta, so 3n into 1 over theta, it will be the differential of the first factor. Now the second factor, we have this will yield 1 over theta square, okay, so we have summation of xi multiplied by 1 over theta square, because d by d theta of 1 over theta will be yielding 1 over theta square, okay, so what we get is minus 3n by theta plus summation of xi divided by theta square, so it is d by d theta of L of theta. Okay. So if you are wondering how we get this positive sign, so here we have the d by d theta of 1 over theta is minus 1 over theta square, okay, and how this is how we get this positive sign, so here we have the d by d theta of 1 over theta is minus 1 over theta square, okay? And how this is minus? Because d by d theta of 1 over theta is equal to d by d theta of theta raised to power minus 1, okay? So minus 1 will become, in front, and d by d theta of theta. So minus 1 into theta square sorry, here we have minus 1, so this negative sign minus 1, it will become outside, and d by d theta of theta minus 1 is equal to theta minus 2, so it will become minus theta minus 2, which is equal to minus 1 over theta square, okay? So d by d theta of 1 over theta is equal to d by d theta of theta raised to power minus 1. So this power, we know that when we have power like d by dx of x raised to power minus 2, so it will become minus 2, okay? And d by dx of x minus 2, so minus 2 x is power minus 3, or minus 2 divided by x cube. This will be the differential. So here theta raised to power minus 1 will have a differential of minus 1 over theta square, or minus 1 theta raised to power minus 2. So this is how we get this positive sign, okay? So minus and minus will multiply and give us a positive sign. So this is the final differential, okay? I am continuing this into the next video to conclude it, or let's do it in this same video because it is 7:40 now. So putting this d by d theta of L of theta is equal to 0. So what we get is minus 3n by theta plus summation of xi divided by theta square is equal to 0. So when we put it equal to 0, we open it. So summation of xi divided by theta square is equal to 3n by theta, okay? So let's convert this theta square into this direction. So we have summation of xi is equal to 3n multiplied by theta square, okay? This is denominator. When it comes to this direction, it will become numerator over here, okay, divided by theta. So theta square will be cancelled with this theta. We have only one theta left in the numerator now. So summation of xi is equal to 3n theta. Now we want to find the theta. So theta is equal to summation of xi divided by 3n, okay? So this can be written as theta is equal to 1 over 3 into summation of xi divided by n, okay? And we know that summation of xi divided by n is equal to x bar, which is the average. So theta is equal to x bar divided by 3. So this is the MLE, or the maximum likelihood estimate of the theta, which is equal to x bar divided by 3. So mean divided by 3 is equal to the MLE of this particular gamma distribution, when we have alpha is equal to 3 and beta is equal to theta. Thank you. These questions are, computationally these are complex. so you have to make a lot of calculations. Okay, unlike the MME methods, because they have very less computation. Here these are computationally complex, so you have to bear with the calculations and all, and you will have to very